Yeah, so my name is Kratarth Goel. Thanks for the introduction. I am a research scientist at Waymo, and the talk will focus on the scaling and distillation of motion forecasting models for planning. The first thing that I want to acknowledge, at the start, like when this workshop was being put together, Drago, who is my senior and like the VP of AI at Waymo, was supposed to be presenting, but due to some issues, he was not able to make it to ICCV this year. So instead, I am presenting this version of the talk, which is also kind of like interesting because I'll be talking about these like two parts to autonomous driving, like the foundational models for autonomous driving, as well as the Distill students. And so you'll get like a real life experience with like how even in the talks, foundational models perform as compared to the students. So let's see how that goes. A little bit about like the PR, I guess, at Waymo. The mission of the company is that we want to be the world's most trusted driver. Yeah, and we've announced, I think, like earlier this year, that we are now serving much more than 250,000 paid trips per week, which is one of the, if not the largest deployments of AVs anywhere in the world. Maybe some companies from China, for example, are like rivaling that potentially. I'm not too sure. We are serving riders everywhere in like actually five major cities in the US, including all of San Francisco, Phoenix. I think in San Francisco, it's like a 300 square mile radius of like the service area, which is pretty sizable. Some of like really challenging scenarios happening all around San Francisco. Same with Phoenix, LA downtown, and like areas around it. In Austin, and also I think like recently we also launched in Atlanta with the same partnership, if I'm not mistaken. So yeah, we are growing and accelerating in our both like the regions that we are operating in and like the volume of rides that we are providing in all of those regions. There are also a lot of like other territories that are partially announced at like different phases of our deployment. Like the ones in like these blue green stars are the cities that I already talked about, which we are like fully giving like rider basically driverless services already in. And in blue and white dots represent some of the cities that we are like testing in for potentially future deployments. A couple of other things that actually I'm very personally very excited about is like we also announced like we are going to London, which is our second international market after Tokyo. I spend a lot of time in London myself, especially during the winter, so I know it can be like a really challenging city for deployment of autonomous driving cars, and it will be like really fun for me to witness that as part of like the journey with Waymo. And at the same time, we are also like now testing it at the San Francisco airport, which is I think our second or third airport behind like Phoenix, where we are already offering rides, and a few other airports that we are also testing on. I think like as I mentioned, like the main mission of the company is to be the world's most trusted driver, and I think like trust happens only with like safety and its metrics. I think like Waymo has been at least one of the leading companies to share like very publicly all of its like safety metrics that are like validated from like third parties that do a lot of like safety analysis for like vehicles in general. And compared to a human driver for the same distance in our operating cities, we find in our like safety reports that over 71 million miles of driverless driving, way more results, 8% fewer crashes or injuries. Actually, there are like three kinds of stats over here, and I believe if you go from the left to the right, you see lowering intensity of crashes, I should say. So the left are the ones where crashes caused injuries or worse, and the middle were injuries where at least airbags needed to be deployed, and in the right were like fewer injury causing crashes, so not that severe. And across all of them, we reduced like the number of these like crashes or injuries caused because of them by around 88% in the worst case, and like around 80% in the other cases. Particularly, I think like one of the most important things for autonomous companies to do would be to like reduce injuries to vulnerable road users, which include pedestrians and cyclists, which like share the road with autonomous driving agents and like vehicles in general. And in this like safety report, we also found out that again, I think like the intensity reduces from left to right over here. So on the left, in the severe cases which caused like really serious injuries to pedestrians, like Waymo was able to reduce these injuries by 93%. And then like I think like right side is about motorcycle crash and injuries, which we were also able to reduce by a pretty significant fraction, which I'm really proud of. Um, some of these like yeah, they're like autonomous driving, a lot of these clips exist, and I think our company handle at Twitter is also like very active in sharing these, so maybe some of you have already seen this. But this like particular instance is like really challenging, I would say. When we roll back, like you'll see that there was a scooterist right over here, and that's like it's night time, so like vision is also like a little bit compromised maybe. But like the scooterist was driving, and then they semi collided with the footpath on the right side. They lost their balance, and uh, they like came in our path of driving somewhat. And like our planning stack and like the overall end-to-end autonomy stack was able to handle this event. Like, this is an RO, like rider only uh, interaction. So the Waymo car at this time did not have any safety drivers that were behind the wheel, but our autonomy stack was able to very elegantly like handle this situation in a matter of like split second, understand what's happening, and like navigate around the pedestrian without causing any harm. At the same time, actually, like why the scenario is also very interesting is that there were, of course, vehicles coming from behind us on the left. So it's like a really complicated interaction where the car has to understand, like, like the pedestrian and like how they are affecting our like already planned future, but at the same time, in its mitigations or like nudging or like swerving around, we also have to understand like what the other vehicles that are approaching us from behind might do, so on and so forth. Uh, yeah, so this is another challenging scenario. Let me see. Yeah, so over here, what happens is that there is this vehicle that will try to cut us in from the right because there is like a braking vehicle in front of it. And again, this is like a completely rider only, driver free. I'm losing out of terms, but you guys get the idea. And we are like driving around, and like the situation happens, and the Waymo driver is able to completely autonomously navigate around like these situations. Again, it's like I've seen these clips like a million times maybe, but I still find them like really amazing of how quickly everything changes on the road. Like these like interactions are really complex, and still like the technology is good enough to be able to like handle these like really elegantly. Already, I would probably not be able to do as well in a lot of these scenarios. There are a long tail. I think long tail has been like talked a lot as part of this workshop. I think like data and like how it is like out of distribution, and like there is like a really thin long tail of driving because there is so much interaction happening. Stuff that you see in like San Francisco every day. Actually, like I think like the definition of long tail is like really kind of complex in itself. It's a long tail definition of a long tail event. You can have like maybe these scenarios happening like maybe once every week in San Francisco, and then there will be like some other scenarios like probably like a barbecue grill falling off the truck on a highway that maybe hopefully happens less often. Um, but both of these are like some kind of like long tail events, and I think like the definition of long tail is also very correlated with the kind of problem you are trying to solve. For example, if you are doing like world modeling or video generation, maybe some of these things are like less long tail versus driving. But really, like I think like in this slide, what we wanted to point out is that you can get all sorts of like crazy things happening on the road, like stray cyclists, toddlers on the loose, running away from their parents in front of autonomous driving agents, falling skateboarders, which I already discussed, barbecue grills, falling trees, flooding, road blockages, which are also like really challenging interactions, I would say, because everything is like happening on the road. In addition, there are like maybe construction people or like police or other like traffic directing agents that you need to understand and like react to. And last minute lane change is something that I already talked about. So as I was like mentioning at the start of this talk, like the Waymo product is scaling at an exponential rate. We are deploying in like so many more cities, like really different, like out of domain like scenarios that we have to handle. And at the same time, to match the scale of our product, we also want our models to be like scaled proportionately. They need to be able to like, because you can only write so many if statements and heuristics. Of course, with ChatGPT or like other, Gemini based self like coding tools, maybe it's like a little more easier, but still like it can only do so many like lines of code because you have to review it and so on and so forth. If there is a video recording, let's edit the ChatGPT part. But yeah, so but I think like as much as less of that we can do, the better it will be. And so we want like our models to like subsume a lot of this complexity and like absorb a lot of like this understanding of the world. So so that is what like the big portion of my talk is going to be about. And then irrespective of how much you can like scale these models, of course you can always build a really complete and like complicated driver in cloud. But cloud is not what is driving the car, because as I was saying, like latency is like really important in like an instance in like milliseconds on the road, and we really want a very competitive driver even on the vehicle. And one way to achieve that is through distillation, which is like a big focus of this workshop, and I will also like touch about it briefly. One thing I do want to mention is like I did say that we want our models to match the scale of our product deployment, but not the complexity. The model should be as simple as possible, in my opinion at least, which makes like scaling for it better. And so I think like with this, I want to transition to like the three main ingredients of this talk. There is a like a scalable, we want like a very simple scalable model family that we can actually like study the scaling laws for. And scaling laws are kind of like a bread and butter thing, very important for us to like take decisions about how much data, what kind of compute capacity of the models that we want to train in order to be able to like handle all of this complexity that I was showing you guys earlier. The second part is like that right recipe of the actual scaling laws, like how do you train these models efficiently with what amount of compute and data. And the third part of this talk is like about distillation, which I already mentioned. So let's start with the first key ingredient, which is like a scalable model family. I think like some of the other speakers were also like talking about this, but this is how like somewhat traditional perception AV stack looked like, at least in the past. It somewhat maybe also looks like it today. There is like a lot of like fuzzy boundary happening now between like raw sensors and like plans coming out of our models. You can think of like these inputs to be either like explicit embeddings of the world, like boxes of agents or traffic light states or high definition maps that are like human labeled or whatever. But at the same time, you can also assume that there is a lot of like implicit embedding, like continuous representations of the world that are being fed from perception stack to the motion planning and motion forecasting and planning part of the stack. But the latter will be most of the focus of this talk, that how do we take the representations coming out from the perception models and like try to scale up the motion prediction and planning pieces. And the outputs look like basically future predictions of like all how the world is going to be evolving in the future, and how we should like take all of those evolution in considerations and like plan around them to reach our goals safely and efficiently. So I think there has been like a really amazing progress in this space. Actually, I think like very far back, like there was like social LSTM, which is like something archaic right now that happened, and then like as a byproduct of it was like multipath and like multipath plus plus, which I think like Waymo was were some of the pub, published works from Waymo that try to take a stab at this place, at this space. I think one thing that is, I don't know, yeah, maybe it's clear, but in multipath plus plus also there was like a lot of like bespoke architecture, like basically like how to design a solution specifically catering to all of like the different multimodality rich amount of data that AVs have, like LiDAR embeddings and like camera outputs and like road graph and so on and so forth, like a lot of like very bespoke architecture, some kind of like attention like layer on top of it, but like very bespoke encoders for all of these modalities. And then more to sequence and like impact and smart, like really smart pieces of like publications that happened. But again, like I think like the trend initially was like really bespoke architectures, especially catering to the complexities of the AV space. And this is kind of like a chart. Like I think like one of the things that I'm also like super proud about at Waymo, like our team and collaborators established this Waymo Open Motion Dataset Challenge that allows academia and like people even outside the industry to try different approaches and see like how they stack as compared to all of these very bespoke AV specific um, uh, approaches to solve this problem. And we see two things over here. One I will mention in this slide, and one I'll come back to later. That of course, like this is what you want to see. Like as time passes, the performance on like this mean average precision metric, which measures how well the predictions of your model are compared to the ground truth trajectories that have been logged on vehicle, keeps improving. So that's great. But I think like what is even more important is like the better lesson, which I'm sure a lot of us in this room are familiar with, that the more structure you put, or like the more inductive bias that you place on the problem, the less intuitive the solutions become. And maybe the right path forward, which I was like alluding to earlier, is that we need like general models that are able to leverage compute and data efficiently. And maybe at the end of the day, like they will be the leading cause of success in trying to solve any problem. So I think this is not specific to the AV word. This is from like a slide from a lecture at Stanford. But basically, like it is trying to convey the point that initially, when a domain does not have compute or data, you start with like you need to be able to make progress, and the only way you do it is by imposing more structure on the problem. That hey, let's have convents because they are fun, and because we had like MNIST and ImageNet, and then we had like all of our like uh, really well liked VLMs recently, which are now trained on internet scale data, and we throw away all of those cons. There was like a resistance for a little while, but now everyone is probably firmly in the transformer VLM camp. And so like less structure happened there, and like exponential learning happened. But that can only happen like organically. And I think like with Waymo, like I think like whatever, like a decade plus a long driving and data collection spree and like billions of dollars, we are at a position where we are ready to explore like less structure and like throw more data and compute at the problem. So yeah, I think like we are somewhere over here right now, where we are trying to remove all of these structures and like add more compute and data and like see like what that can do for our domain. A little bit about our problem formulation, and I think like I really like this way of looking at it. There has been like a lot of advancement in the space of like language modeling, LLMs, VLMs, that all of us are very intimately familiar with. We like at least at Waymo in research, we want to look at driving as like a new kind of language. It is basically really like a complex dialogue where a lot of agents involved are like coming together at an intersection, exchanging ideas, and then like trying to make progress towards the future. And so in this particular work from 2023 in Motion LM, that is what we tried exploring, that how do you model the problem of motion prediction and planning as a language model, essentially, where you tokenize like the sequence of everything that happened in the future, and it's like kind of like a discretizable space. So you have like this vocabulary of actions that each agent can take at a particular timestamp, and then you like make predictions over that vocabulary, very similar to like RLLM literature. This is like a work that predates it. It's called like Wayformer, where that was the application. So there are two parts of like trying to look at our problem in a LLM kind of a way: the problem formulation of the task itself, which is autoregressive discrete token prediction, I would say. And the second part is like how do you employ the transformer backbones to solve those tasks. So we did like two of these works, like Motion LM and Wayformer, that allowed us to get like most of the way over there. And like there has been like a lot of progress in this space since then. Also, like in terms of problem formulation, like there are two kinds of ways in which you can do this prediction. One is like marginal, where you just want to predict independent of how the world is reacting to you, how your own trajectory in response to the current and past state of the world should look like. So that's the marginal prediction. And the causal, like the joint prediction, is kind of like a causal dialogue. So going back to my language analogy, the thing on the left would be that what I am probably doing right now, I'm not considering any of your reactions, how many of you are falling asleep and need coffee or whatever. I'm just like making like a speech. And the other would be probably what happens at the end of this talk, where like people are asking like question answers. So it's more of like a collaborative interaction, which I hope we have time to get to. The other way of also like doing the same kind of modeling is like conditional, where I condition on like someone's speech and then like react to, or like maybe this is more also like question answering. I'm not sure about that analogy. And a lot of these can just be implemented as a change of the attention mask, basically, of what you want to predict and what you show your model when you are like employing that transformer to solve this problem. Yeah, so I think like this is sort of well understood. And then like there is like the at the time when you are able to like accomplish this, the parallels to like language kind of like only keep growing from there. Like you can have like a lot of like rollouts, you can do a lot of inference scaling and then cluster like all of the modes of like what is going to happen in the future. So I think like what we are displaying over here is very typical of what we want to do with the Waymo open motion data set as well, where we set the limit of like how many modes you want to submit to compare against the ground truth, and I think they are set to 6. So that is what we are showing over here. And then you can make as many inference time scaling predictions of like infinite trajectories if you want, cluster them down to 6, and that is what becomes like the operating like modes of prediction from your model. So that's about like the simple like model family. And the next part of this talk will focus on like how do we like scale it correctly. So the first part is that can we actually scale it? We've seen a lot of parallels in language. Actually, I gave away the answer, so sorry for the spoiler. But we've seen like a lot of like scaling is possible in language models. Like hundreds of billions or even trillions of parameters of language models are already being trained on trillions of tokens. And can we do the same for language? So this is our attempt on doing something similar. We published this like recently this summer, and we saw that like yes, the scaling evidence does hold. So what you see on the y-axis is just like some kind of like perplexity or negative log likelihood loss on predictions of these like discretized action tokens, and on the x-axis is like the number of training flops. And we saw that if you are like training models compute optimally, as that overall training flops improves, you get this like nice like scaling trend. The first order bit of like take away from this plot is that more compute results in like lower loss. But more importantly, you can also fit like a log linear power law kind of like a result to all of these experiments, which is like really which is really exciting. Some of the similar work also happened like in language before us. This is like roughly the formulation that basically unconstrained by basically the parameters of your model and the size of the data. If you scale compute, the loss of for your model should like decrease as a power law, as I was previously stating. In order to get to these results, we basically train a bunch of models in a isoflop compute optimal way. And so what you see on the right hand side is like basically like parabolas emerge. Each parabola has a fixed amount of training compute, and where you are training a family of models with like different amount of data and capacity. And what is really interesting, as happened in language, that a compute optimal model emerges, which is at the bottom of that parabola. And if you look at like all of those compute optimal models, you can fit basically like a log linear plot through all of these like black points or black dots at the end of the parabola. I don't know if you squint enough, you can see this like log linear trend emerging almost. And what the conclusion that we can make out of it is like basically, in order to like increase my compute 10x, how much of that compute should go in investing in getting more amount of data versus how much of that compute should go in increasing the capacity of our model. And in our scaling laws, at least in this initial version, we find that 10x compute should mean roughly 4x parameters and roughly 3x the amount of data. The same fits also allow you to make a even more spectacular statement that even the loss, even before training a model, you can conclude that if you do this correctly, if you follow this recipe correctly, what the loss will look like as a function of compute, as I was mentioning previously. But of course, like this log linear fit is like a little bit of a lie, because if you look even more closely, you see that all of these orange points that we are trying to like fit this curve to actually have like a little bit of like a curve in them. And so if you like add this irreducible loss term, we are able to fit those points much better. And then the next natural question emerges that what is the reason of this irreducible loss, and is this something to be scared of? I would say no. There are probably two reasons of this: aleatoric and epistemic uncertainty, which basically like the aleatoric uncertainty is about there is an inherent uncertainty in being able for us to be able to predict the future, because people do random things at any point of time. And epistemic is like basically the limitations of our inputs that we are feeding the model. There is always some unknown, and so like that is something that we can probably do better at. This can also be a good motivation of training end-to-end models, like I was showing for this falling scooter kind of like example. More, there are like some examples which in the interest of time I'll skip, but basically we were able to observe both qualitative and quantitative wins when we trained like larger models. Over here on two sides, like we 24x the compute, and we are able to see that like the in red is the ground truth and blue green are our predictions. And we are like with scale we get like models that actually are able to fit this data distribution much better. I think like one other like really big fear in robotics in general is that like you can scale in open loop, but there is like this train rescue or covariance shift or dagger problems, where when you are like unrolling your trajectories in closed loop, there may be like an accumulation of errors, and your like models basically slowly drift away from the training data manifold and get into like this unknown like uncanny valley, and like then they are just like completely out of domain and can screw things up. But very interestingly, for like this study, what we found is that if you do like simple scaling with like no informational bottlenecks, the model is actually able to scale. And we see like a similar kind of like a power law fit with a irreducible loss emerge even in closed loop. The definition of the closed loop is like kind of like a little maybe complex over here, but for more details, like I will ask you guys to like refer the paper. Nice. So yeah, this is like one of the examples where the model is now running in closed loop, and maybe like the visualization is not that precise, but what is happening here is like there is this vehicle that emerges from the parking lot in closed loop. The model is able to uh, wait for it, allow it to like merge into the traffic, and then navigate around it. This is all without closed loop training or reinforcement learning being introduced anywhere, just through imitation. With correct like scaling behavior, we can already see these emergent behaviors happen even with our data. That is not to say that we don't need closed loop training or reinforcement learning at all, but it like if we can get this just through imitation teacher forcing, it's already like a very powerful model to then do post training on top of. Another example of like complicated merges, so that's good. Yeah, have you out of time? Or?
We have only 5 minutes. If you want to give Q&A time for the
audience. Oh, okay. Yeah. So that's about our scaling recipe. I definitely want to leave time for questions, so I'll breeze through distillation. So yeah, I think like scaling up, as I was mentioning initially, that scaling up is like really important because it allows us to have like a really like a good starting point to do fancy stuff on top of. But again, like these very large models are probably not suitable for the vehicle, and for that you need to be able to distill this recipe down into a smaller student. The way we do it is basically you have like a Gaussian mixture fit for the expert over all of its distribution of representation of the data. You do the same for the student, and then you can like minimize the KL divergence between both of these distributions potentially. And what we see, like this is also like a published work from 2024, where in the blue we train all of these like very large teacher models, and we train an ensemble of it through some kind of like inference scaling almost. And you see like the results are tapering off, but as you increase the relative flops of the ensemble of the teacher, the mean average precision keeps improving. If you distill it down into a single student, you are able to get a student that is like much cheaper, but still retains most, I think like around 98% as good as the ensemble of 20 teachers, which is very exciting. So in summary, we went over that you need like a very simple model that you can scale. Then you do a lot of scaling laws on top of it to get the right recipe of how many parameters, data, and compute you need to like train really amazing models. And then very quickly we went over like how to distill these models to smaller students. We are hiring as well, and so we have a booth and everything. Look at these QR codes and like follow up as needed.